In this video, I will show how we can construct a mosaic from an underwater video taken by an underwater robot. I will use an interval analysis approach. So this presentation has been presented at the CTech Week. This work has been done by Mateusz Larangera and a part also by Clément Aubry on the loop detection. And it has been supervised by Luc Jolin and Sébastien Tauvry. So what is a mosaic? I have a video, and from this video, which has been collected by an underwater robot, I have to build a big image which represents of all the area that has been explored by the robot. I will present now the loop detection problem. Why the loop detection problem is important for localization when a robot is moving inside an environment, unknown environment. Then, in order to be able to avoid to be lost, it has to make loops. Doing loops, it will find back some zone he has already explored, and from this, it will be able to relocalize itself. So in order to not to be lost inside an unknown environment, it is important to make loops. This will be illustrated later. First example is we are driving a car in the desert, and we have no landmarks, nothing, only sand. And we measure the speed of the car, its orientation using a compass. And we have no GPS, no cameras, no other exteroceptive sensors. Is it possible from orientation and speed, I mean only using proprioceptive sensors, is it possible to count the number of loops? So an example I can give here is a classical book from Tintin, which is the Land of Black Gold. You have Thompson and Thompson, which are moving with their car, and they are totally lost. And due to the fact that they make loops here, they have the feeling that they have found their way. Of course, it's an information to make loops. But here, of course, they make a mistake, which makes the story funny. They make a mistake, and in fact, their car perform a limit cycle. Of course, it will not be the case here, but it illustrates that if you make loops, you have some information on your trajectory. A robot can be described by a state equation. So x is a state, f is the evolution function, and u is the inputs. For us, here, it's not a control problem we'll deal here. U is known. It is the proprioceptive sensors. It will be, for instance, for an underwater robot, it will be the speed of the propellers, or it can be also the orientation obtained by a compass, the speed by odometers, and so this describes the dynamic of the vehicle. And the exteroceptive sensor is y. So y is a function of x. To detect loops here, we'll only use this equation. We'll use only the proprioceptive sensors. And we'll show how is it possible to detect loops using only proprioceptive sensors. It is the work of Clément Aubry. So why we do not believe that much exteroceptive sensor? Imagine that in your robot, underwater robot, you have a camera, and you see this below the robot. at time t1. And at time t2, you see that. Now you want to know, with this exteroceptive sensor, with the cameras, you want to know if you made a loop or not. I mean, is this area correspond to this area? So first, what can we do with a vision algorithm? We detect interest points, like this one, using, for instance, a surf algorithm. Then we eliminate all outliers using a ransack algorithm. And if the number of correspondence is good enough, we can say that maybe these two images are compatible and maybe it corresponds to the same area. But are we sure we made a loop? No, not at all. So I will illustrate this here. Assume that you have a camera, so it's not an underwater camera, and you see this. The robot is moving, and later it sees that. This corresponds to that. Here you can see that this image is compatible to this one, and you may say that this corresponds to that, and you make the correspondence. But you are not sure. It is not because the two images are compatible that you can associate this to that. For instance, in this example, this is not this one. This one is that one because of this situation. Or in practice, we can see that two images are incompatible, but we can never prove that they are compatible. How can we prove that two images are compatible, and how can we prove that this one is the same as that one? What will be shown here. So for this, we need a theorem, but we need first to introduce the notion of t-planes. What is a t-plane? A t-plane is represented here. I have my robot which is moving. At a time t1, it is here. So t1, and it continues. It makes a trajectory or whatever. It comes back, and at time t2, it is here. We made a loop. I mean, the position at time t1 is the same at time t2. How can I represent this single loop? First, I define the shift function. So the shift function is a displacement of the position between time t1 and time t2. It corresponds to the integral between t1 and t2 of the speed of the robot. We now define the loop set. The loop set corresponds to all t1 and t2, all pairs t1, t2, such that this displacement is equal to 0. Of course, I will assume that t2 corresponds to the future and is after t1. So it is represented by this inequality. So here I have time t1, t2. It corresponds to what we call the t-plane. And here I have t1 equal t2. So if I take here t1 and t2, the pair t1, t2, my robot is here at time t1, at time t2, and this vector corresponds to the displacement, to the shift. When the shift is 0, it means that you are here, and it means that the t-pair corresponds to a loop. So in this example, I have the t-plane, which is here, and the trajectory here. As we can see, there is one loop here, it is a small loop. Here I have another loop, and as we can see here, there is a more complicated loop. So this one corresponds to t1, t2, which is here. So of course, when I am in this line, it means that t1 equal to t2. I cannot be here since t2 should be greater than T1. So this one is smaller. It means that T1 smaller than T3, T4, and so on, and T2 the same. This one corresponds to a small loop, this loop. But this one corresponds to a case where the position at time T3 here corresponds to the position of the robot at time T6 here. And we can see that this one, in this situation, T3 is smaller than T4, which is smaller than T5, which is smaller than T6. It means that the interval T3, T6 enclose the interval T4, T5. So, equivalently, this point dominates this one. Or, if you want, the interval T3, T6 enclose T4, T5. So when a point, T point corresponds to a loop is this direction, and it means that it dominates the other one, so it encloses them. This loop, big loop, enclose this loop. Okay. Now recall that in our problem we want to prove that we made a loop, and we want not only to prove this, but we want to use it in order to relocalize the robot. The main theorem that will help us to solve the problem is the Brouwer fixed point theorem. So it is an old theorem which states that any continuous function, I call it n as Newton, but we'll say later why. Any continuous function n from a bounded convex subset of Rn. So for us it will be a box. It can be a sphere or a disk, but for us it will be a box. So if the image by n of this set is included in itself, then n has a fixed point. A fixed point means that n of x is equal to x. So if the image of a box by n is included into itself, then we have a fixed point. I have here an illustration. I have a box. It is a convex set, and I am working in R2. Let me take this box. I have some distortion represented here, a distortion. I have an homotopy, so a narrowing, an homotopy with a coefficient which is smaller than 1. I have a distortion, not a folding. Let me fold this shape into this one. It means that this point goes here. Oops, sorry. Goes here. I translate and I shift it. I obtain this. And then I have an homotopy. So I enlarge it. And in fact, I can do what I want, such as narrowing, folding, shifting, and so on, if the image by the transformation of this box is included into itself, as it is the case. Then it means that at least one point here has not moved. For instance, maybe this point has been mapped into this point, but one point has not moved. We don't know which one it is, but one point has not moved. It is a Brouwer theorem. Okay. So let me take an example. I have a function n from R2 to R2, which maps T1, T2 into this vector. Of course, the cosine sign means that it will always belong to -1 plus 1. So I know from the nature of this function that the image of a box T1, T2, excuse me, yes, minus 1, 1, 41, minus 1, 1, 42, it's a box in the T-plane. If the image of this box, here it will be included into this one, and I have this because of the cos and sine, which are between minus 1 and 1. Since I have this, I conclude from the Brouwer theorem that there exists at least one T1, T2 inside this box, such that n of T1, T2 equal T1, T2. It means that n has at least one fixed point inside this box. So for us, for our loop detection problem, I want to prove that the deep displacement is zero. So displacement of T1, T2, here it's written x, is equal to zero. So I want to prove that I have a zero of the function. Zero means a loop. I can associate a fixed point function, for instance, a Newton function. Most of the time it can be something else, but here I take the Newton function. Since I have with the Newton function, I have this implication. If x is a fixed point of n, it means that the function, that x is a zero of f. Then, using the Brouwer theorem over n, I can prove that the image of a box is included, so the image of a box by n is included inside this box. Then it means that I have at least one zero of the function. So I have one loop. Okay, so let me give you an illustration. I have here x1, x2. Here f1 equal to 0. Here f2 equal to 0. The solution here is 0. What the Newton operator does, I take here gridding for illustration, and the image of the gridding corresponds to this. It means that the image of the big square corresponds to this, and here, since this is included in the previous square, from the Brouwer theorem, I have at least one solution. Of course, I may have several solutions, but here I have only one. Brouwer theorem that say that I have at least one. Interval analysis will help us to prove that I have the Brouwer theorem applied. So let me recall some basic notion of interval analysis. If I have a function from Rn to R and a box, Cartesian product of intervals, interval analysis is a tool that makes me possible to prove that for all x, this function is positive. Okay, of course it should be the case, but if it is the case, that interval analysis is a very efficient tool that makes me possible to prove this. Let me take an example. I have this function, and my equation is this function includes multiplication, totally nonlinear, non-monotonic, minus cos, sine, so trigonometric function, and so on. My equation is this function always positive for x1, x2 inside this interval? That's what I want to prove. How can I prove this? I can prove this using interval analysis. So let me show you how. First, I define the interval arithmetic. Interval arithmetic, I can define multiplication, addition, sine, and so on. All elementary functions can be extended to intervals. Let me, for example, illustrate the multiplication. If A belongs to this interval and B belongs to this interval, then A times B will belong to this interval. For instance, A times B can reach minus 5. Minus 1 times 5 corresponds to minus 5, so I can reach this. I can also reach 15. 3 times 5 is 15. So I can define the multiplication, addition, and so on for interval. Everything that can be done for real number can be extended to intervals. So let me come back to my problem. The interval extension of this is obtained by replacing all operation by the interval counterpart. For instance, here I take the same expression, I replace x1 by the interval x1, x2 by the interval x3, x2, and I apply interval arithmetic rules. Moore has proved that if the image of this interval extension is positive, so it's included in positive real numbers, implies that for all x belonging to this box, f will be positive. So I am able to prove that over a box, the function is always positive. Okay, so now the Moore-Brouwer theorem. If the image by a function f from Rn to Rn is included in X due to the fundamental property of the interval extension or inclusion function, if I have this, it means that then there exists an X, at least thanks to the Brouwer theorem, which is a fixed point of f. I will use this to prove that I have loops. Okay, what can I do else with interval analysis? I can characterize sets. Let me show you a very simple example. I have a set X, which belongs to Rn, which is given by inequalities, and I want to bracket it by subpavings. So subpavings is union of boxes. So I want to find two subpavings, x minus x plus, such that I have this inclusion. I have an approximation from inside of X, but also from outside. Or let me show you how this can be done. I take my X given like this, or given by the same expression, and I take a box. For instance, this box is, I apply interval arithmetic. Whoops, sorry. I apply interval arithmetic, and if for this box, if the image is positive, so the interval of the image by the interval extension is positive, then I know that for all x inside, I will be positive, and the corresponding box will be painted red. If it is negative, it will be painted blue. Otherwise, I will bisect it. So using a very simple branch and bound algorithm, I will be able to characterize such a set with an arbitrary precision, arbitrary accuracy. It is what I will apply for loop detection. So, loop detection for uncertain trajectories. I have a robot and I know a tube for t. I mean, I know a box for each t enclosed which contains the speed vector. Okay. So, the set of all t pairs such that there exists a function v inside this tube, such that the integral, so the displacement, is equal to 0 with t1 smaller than t2. If t satisfies this, it means that t1, t2 can be a possible loop. So I translate this into inequalities, and to say this means that for the lower bound, I have to be of this interval, I have to be negative, and for the upper bound, I will be positive. In such a case, I will know that for a V inside V, I will be equal to 0. Okay? So, in fact, this makes me possible to translate my loop detection problem into inequalities. This inequality involves two variables, t1 and t2, and this t1, t2 corresponds to the bounds of the integrals. Here for the lower bound of the tube V and the upper bound of the tube V. So if for t1, t2 I am smaller than 0, it means that I am inside the tube T. Okay, so now let me show you a test case to illustrate. I have a robot, the red armor, which is represented here. And this red armor has started here. It moved in this direction, and an approximation of the trajectory is given here. It does not mean that it is a true trajectory, but just an estimation of the trajectory. But here we can see a tube approximation. So it increase and increase, and you can see the pessimism increase. And after 2 hours later, I am totally lost. Totally lost means more or less 200 meters. Okay, at the beginning, I know where I am. After I am lost. But I made loops. I made, for instance, a loop is here. Another loop is here. Another one here. I have 28 loops. If I count for the estimation, I have 28 loops. It does not mean that I don't know exactly how many loops. Maybe here, for instance, I have a loop. I don't know. Because I can guess that maybe I have one, maybe not. Here in the illustration, I have no loops. But I have some inaccuracy. And maybe I have 2 other loops here. Okay, so I want to count in a guaranteed way the loops. If I use the algorithm, I will obtain a set of all feasible loops in the t-plane represented here. On the left, you have the t-plane. When I am here, you can see I have a small trajectory. T1 and T2 are almost the same. When I am here, T1 and T2 are almost the same. Again here, I am almost at the end of the trajectory. So the end of the trajectory is here. Okay, here. Here I am at the beginning of the trajectory. There. This is the beginning of the trajectory. Here I have many possible loops. For instance, if I am here, I have a big loop. Whoops, because I have to do a lot of it takes me a lot of time to go from T1 to T2. So this is a big loop. Another big loop is here. Okay. And small loop are here. It is a small loop. Oh, let me zoom on this loop. So this loop, it was this one? Yeah, it was this one. So let me zoom here. Up. It was this one? Yes. Zoom again, zoom again, zoom again. This is a loop. Okay. The small loop, which is here. I have a lot of possibility for being a loops. What is sure? Whatever the uncertainty of the speed, I am sure that I have only one loop. I don't know which one it is a true one, but I know that I have only one loop. So I can apply the Newton operator or the Brouwer theorem, and it finds me, so several times there is a specific algorithm developed by Clément Aubry, which is called the Newton inflation, and it gives me a square. If I apply to this square the function f, so the Newton, the Newton operator, then I will be included into myself. So it means that from the Brouwer theorem, I know that I have at least one loop. Moreover, I can show using the Banach theorem that this loop is unique, but I know that I have at least one loop here. So it is written somewhere here. The Newton of a box is included into itself, so I have a proof that I have at least a loop here. Okay. Okay. So now how can I use this for doing a mosaic? A mosaic, I have a small experiment that has been done by AUV of ECA. So the AUV underwater robot starts here. It goes there and there. It continues here and goes here. So it makes loop here, of course. Come back here. Oops. Go there and there and there, and at the end it finishes here. So of course, when you have here it corresponds to a loop, a clear loop that I can use to improve my trajectory. This part here corresponds to two trajectories that are, at least for a piece of time, that are parallel. That's why I have this. It is the degenerated loop. I don't know, here also I have a part of generated loop. So let me, I can use this. I can take, for instance, a part. So I don't know which loop is taken here. But maybe let me consider, I will take only in the t-plane T1, T2, which may correspond to loops in order to improve my trajectory. So let's take me a point somewhere. I have this. Am I compatible or not? So I have some specific algorithm that can be considered as reliable, that can tell me this one is or is not compatible. When it is totally different, for instance, you have sand here and there you have rocks, I will tell you, no, it's not the same. But when you have a thing like this, they will tell me it is compatible. But when it is compatible, it does not mean that it corresponds to the same area. So how can I prove that it corresponds to the same area? So in the t-plane, I have some sets like this. And I have applied a Newton operator. And the Newton operator told me, here you have at least one loop. So I can test all t pairs. Okay, I test all. This one not compatible, not compatible. And here it is compatible. Here it is compatible. So imagine I have two pairs that are compatible. It means first that I can remove all this one and it corresponds to a contractor. It tells me that I remove all them that are not compatible. But I can do more. Since I know, so if I remove all that are not compatible, then I can contract my trajectory. But I can do more. Here I have two that are compatible, but imagine that you have only one. Since I know from the Brouwer theorem that I have at least one which is compatible, and because other one have been eliminated, this one is compatible, then since there exists at least one, it means that this image and this image correspond to the same area. So I have a proof that this one corresponds to this one without ambiguity. And this is new. This is new. Okay, so of course, I have my trajectory. I have the tube, which corresponds to an uncertainty. And since I know that for one point, the point I have shown before, which corresponds to this loop, I can associate this image to this image, and I have an equality. So I have equality relating the state, the position at time t1 and that at time t2. Thanks to this inequality, I can contract the trajectory. Okay, and it is since my position increase, I can be able to build the mosaic. So how in practice is built the mosaic? First, I have the projection. I have my AUV. It takes, we assume that the ground is flat. I know my, thanks to the DVL, I know my altitude. Thanks to my inertial central, altitude central, I know my Euler angle. So I can compute this point and this point, and I can correct my image by projecting by the image I have got by the camera, by projecting it into the plane. Okay. Next step, I have obtained such a thing, and I have to do some image processing, for instance, elimination, equalization to avoid all this. Of course, the trajectory has been corrected. That's why the superposition could be quite good. And after the equalization, I obtain such an image. Of course, if I do it everywhere, I will build an image which corresponds to the mosaic. Here I show the program that has been made by Mateusz. So on the previous example, here the trajectory with the t-plane. The robot is moving and builds the mosaic real time. We can see that the algorithm equalization illumination is applied also in order to have a nice image. The robot is moving and will soon, so I will go later, before the loop. And when he will make the loop, you can see that the image are moving thanks to the rolls and the pitch of the robot, but the projection behaves well. And here, the loop is performed, and the trajectory of the robot can be improved.